Hi, I'm Chem's best friend. If you need any chemistry help, the information is on the bottom of the screen. So hello back. This is the last video in a series of energy, about topic of energy. And in my previous video, we talked about how do you calculate enthalpy? How do you calculate enthalpy of a reaction? Well, number one, you can go to the back of a classroom and do an experiment using a calorimeter, constant pressure calorimeter, and you can actually do it. Many times you would be doing calorimeter, many little steps of a overall reaction, so you'll be using Hess's law to add different smaller reactions to get the overall reaction, which might be too hard to do in a lab. But what if you're going to use the idea of Hess's law and using the back of a textbook as your appendix, using heats of formation? So let's look at my screen and talk about the things. So how do you calculate enthalpy of a reaction using heats of formation and using bond enthalpies? So here is the example that we will use throughout this video, and that is combustion of propane. So this, oh my gosh, I hope this doesn't happen, right? So propane is our barbecue tank, and here is propane burning. A little too much, but here is combustion of propane. So propane is, formula is C3H8, a combustion reaction combining with oxygen, making a carbon dioxide gas and water vapor, and we want to know what's the heat enthalpy of this reaction. Now, if you look in, Google it or look in the back of your textbook, this is the number of this reaction as written per 1 mole of propane. So this is where we will be comparing this number. And I wrote it in a cloud for us to just keep it in mind. All right, so let's start. So here is the tables in the back of your textbook saying these are the standard enthalpies of formation. Standard enthalpies of formation. Now, what does this mean? So chances are many of these are negative numbers, you can see. And this is energy released when you form whatever compound, whatever compound you look at. Energy usually is, how about we'll say energy change. When you form 1 mole of this compound from its elements in the elemental state. Okay, so this will be if you take solid carbon and you take O2 gas and you're going to combine them to form carbon dioxide, this one will release energy. So how much energy is absorbed or released when you form that compound from its individual elements? That is the heat of formation. That's the definition. And I highlighted a few things because, well, here is our reaction. So we're going to look at propane, oxygen, carbon dioxide, and water. Water gas state is important. So let's find here. So here is our carbon dioxide gas and heats of formation. Here is our heat of formation for propane. And here is heat of formation for water vapor. Also, please notice that you need to pay attention to the states because water liquid is a different number. And you say, well, where is oxygen? Oxygen is not on the table. Oh my goodness. But so let's think about it. How much energy will be required to make O2 gas? Well, how does O2 gas exist? How does oxygen exist already at room temperature? Oxygen already exists as O2 gas at room temperature. So you do not need to do anything with oxygen. Oxygen is already in its elemental state. So the heat of formation of O2 gas at 25 degrees C or 298 Kelvin is 0. This is why it's not in a table. So elements in their elemental state at room temperature, heats of formation is 0. Okay, so we're going to look here, and here is important. Here's my reaction that we are doing, and here is the formula. Heat of formation is going to be, you will add up, right, the summation and all the coefficients of heats of formation of products minus summation again, you will add up all the heats of formation of reactants. Remember delta, what does delta mean? Final minus initial. What's your final? My final is products. What's my initial? Reactants. It's my products minus reactants. So what is this N? Well, I'm going to look at, here is what's my products? First, I looked at CO2. Here is heats of formation of CO2 gas. But I have how many? Which is given to me kilojoules per mole. How many moles of CO2 gas do I have? 3 moles. So this is my CO2 gas. It's 3 moles times 393.5 kilojoules per mole. Maybe I should write this. This is my CO2 plus, what do I have? Water, H2O, right? H2O, and I have 4 moles of water. Here's 4 moles of water, yes. And this is negative 241.8 kilojoules per mole. Then I have minus, what's my reactants? Propane, C3H8, and this is my O2, oxygen. So I have propane is 1 mole. Here is my 1 mole of propane, and the number from the table, and oxygen is 0, remember. So I then plug the numbers in, 3 times 393, 4 times 241, here it is, I plug the numbers in, and I get negative 2043.85 kilojoules. So remember, it's my products minus reactants, and that's the number I get. And wow, this number is very, very close to what I just kind of looked, right? I mean, just no decimal points. Okay, that's great. So that's another way, using heats of formation. What about using bond enthalpy? So what's the bond enthalpy? Bond enthalpy, you get a table from the back of your textbook, and you will have basically the amount of energy required to break the bond. Remember, energy is always required to break a bond. Energy is always released when you make a bond. It should make sense. If I'm going to break a piece of wood, energy is required for me to break it, right? So energy is always required to break chemical bonds. And I highlighted some because for my reaction, here is my reaction. The formula is this. The enthalpy of a reaction using bond enthalpies is you're going to add up all the bonds broken minus add up all the bonds formed. So this is my reactants in a way minus products. Now why? Because bond enthalpies are always positive. So this is not our reaction. This one is methane. But let's think about what we're doing. We're going to break, right? Break propane apart, break oxygen apart. We're going to have to input energy in. And then we're going to make CO2, and we're going to make water, yes? So this will be bonds making. Bonds breaking, we have to input energy in, bonds breaking. Now, if this arrow is longer than the breaking, we will have exothermic reaction, which we will have in this case because we know it's negative number. So remember this is your formula using bonds enthalpy. If you are taking AP chemistry test, you have to write this formula on a free response question if you're using it. Okay, so I wrote our reaction. Here is propane, oxygen, making carbon dioxide and water, and I drew the molecules here for us. Here is what propane looks like. Here is oxygen, carbon dioxide, and water. And we're going to add up. Let's break up all the bonds. Well, what's going on? I have one CC bond, and here is another carbon-carbon bond. So I'm going to break 2 CC carbon-carbon bonds, and I only have 1 molecule, right? 1 mole. You can say 1 mole. So how many bonds? How many moles? So I wrote here 2 bonds, and I looked back at the table. So we just kind of looked back at the table right here, 348. So 2 bonds, each one is 348, and I have 1 mole. So just to break 2 of these, 1 mole of my molecule, this will be this much energy. I have 8 carbon-hydrogen bonds, and I have again 1 mole. So I did 8 times 413 times 1 mole. This is just to break CH bonds. And I have oxygen. Oxygen is a double bond. I have, each molecule has only 1 bond, but I have 5 moles of these molecules. So 1 times this times 5. And then I'm going to add up all the energy required to break up all of these bonds. Going to be breaking up, and remember there's 5 of these. So I'm going to add up, and I'm going to need 6,475 kilojoules of my energy is needed to break it up. Okay, what about how much energy will be released when I make new bonds? Well, again, each carbon dioxide molecule has 2 carbon-oxygen bonds, and I have 3 moles, right? So 2 of these bonds times 3 moles. I'm going to write this down. Here is 4,794 kilojoules. And then I make 4 moles of water. Each water molecules have oxygen-hydrogen bonds, but I have 2 of these bonds, and 4 moles of water. Here is my amount. I add up how much energy is released, and I'm going to get out 8,498 kilojoules. So I look back at my overall equation. Here it is, bonds broken minus bonds formed. I write this down. Here is my bonds broken minus bonds formed, and means negative. I get released negative 2,023 kilojoules. All right, let's now remember, this is the number we were shooting for. Let's compare the 2 methods. So using heats of formation, we got this number, 2,043.85 kilojoules, very, very close to what, if you Google it, what it is. Using bond enthalpy, we got pretty close, but this is better. Now, why? Let's think about why using heats of formation is better than bond enthalpy. Here is the answer. Do you see right here? Here is average bond enthalpies. Some bonds a little bit different. So like if you have carboxylic acid, the OH bond will be much easier to break than the OH bond in water, right? So if you have so this is average bond enthalpies. So sometimes bonds are easier to break based on what the functional group is. And also, do you see the states? Do you see gas, liquid here? No, it's just bonds. Remember, using heats of formation, we had to pay attention to states. And we don't here. This is just average bond enthalpies. So average bond enthalpies is a really good estimate. It's going to give you close. But using heats of formation will be much closer, will be much more accurate because you're using average bond enthalpies. So is this making sense? How to use the 2 methods and how they compare? I hope so. And I hope this makes sense. And thanks for watching, and see you next time.